Okay, I said it was coming and I meant it. Section 5.4 is the fundamental theorem of calculus, and it picks up with where the last section left off, and that is with the definition of an average value. Now, what that average value means is there's some point in between A and B so that the area of this curve underneath the blue curve ends up being the area of the rectangle found by the average height, f of c. Okay? So that gives us this formula then, and we could take that height times the base, looking at the area of a triangle. This is the height times the base, or let's say the width. Of this rectangle that actually is equal to the value of the area under a curve. Once again, if I took my spatula and I started smoothing all the way over, this blue part that's up above this pink line would eventually fill in the gap that's below the pink line. So the areas would be the same. All right? Theorem. I don't know how I got this, except I think I started with the fundamental theorem of calculus part 2, because when I first learned calculus, this is what I wanted to get to, because this was the good part. I said we'd be able to find those areas without knowing the formula for the area of a trapezoid, and here's, how we do it. Remember, this capital F is the antiderivative, and we know how to take antiderivatives. Okay, so what we do is we take the antiderivative of this integrand and we plug in our upper bound minus the antiderivative evaluated at the lower bound, and that gives us the value of that definite integral. So what we're going to do now is on the interval from 1 to 3, I don't want to find the average value. I'm going to change the problem. Ooh, no I'm not, because I know what we're going to do. Remember the formula for average value? That's why I put this in here. I had to remind myself. We have a formula that said f of c times b minus a is equal to the definite integral from a to b of f of x dx. We can evaluate this right here. We had a theorem, up here that said that the average value is just 1 over b minus a times the integral. So we could use this, to find c. One over b minus a is equal to the average value of the function. Okay? All right. So, what is a and what is b? Or how would I set up my integral here? We're looking at the integral from 1 to 3, because that's our left bound and our right bound, lower bound and upper bound. And then our function is 9x to the negative 3 dx. And I chose to write it this way because we learned a power rule for integrating, right? That made life easier. When I integrate this, or find the antiderivative, we're going to end up getting 9. Remember, you've got that constant multiple rule that says we can pull the constant out. Right? So this is going to be 9 times, when I find the antiderivative of this, I add 1 to the exponent, so that's x to the negative 2. And I divide by the new exponent, right? And then I'm going to evaluate this from 1 to 3. Right? I haven't done that yet. I'm just trying to take care of this part first. And then I'm going to do that. Okay? All right. Okay, here we go. So, according to the fundamental theorem of calculus, by the way, once you find the antiderivative, notice I put a bracket here. My lower bound is here, my upper bound is here. That means I need to evaluate this by applying this fundamental theorem of calculus. We're going to find f of b minus f of a. So this is going to be 9 times our antiderivative evaluated at b. Well, this is negative 1/2 times 3 squared, which is 9, minus negative 1/2 times 1 squared, which is 1. Okay? There's a step I probably should have included to make this make more sense. Yeah, hang on. I'll show you. Right here, what I did was I rewrote this as 9 times negative 1 over 2x squared. So I got rid of my negative exponent by moving that x into the denominator, and the 2 was already in the denominator, and you just take the negative that's in the denominator and put it out front. So then what I did was I just plugged in my upper bound right here into that antiderivative, and my lower bound right here into the antiderivative, and now we just take care of the arithmetic, right? So this is going to be 9. I'm going to need more room, I know. This is going to be 9 times negative 1/18 plus 1/2. Right? Yes, no, maybe. When I distribute the 9, I end up getting negative 1/2 plus 9/2, and negative 1/2 plus 9/2 is 8/2, which is 4. Which means that this area from 1 to 3 is equal to 4. Now I've got to find the average value. Yeah, it's going to be 1 over b minus c times b minus a times this. So the average value, which is what we were asked to find, is 1 over b minus a of that integral, which we said was 4. So this is going to be 1 over 2 times 4. Half of 4 is 2. So this is the average value of that function in that interval. Right up here, and there's our a and b, that's our upper and lower bounds, times the integral. What I did was I evaluated the integral first, and then I went back and I plugged in the multiplied by 1 over b minus a. Okay? Any questions? Next problem. Evaluate the integral from 0 to pi over 2 of 1 minus cosine 2t dt. Do we have a double angle formula that we can use to simplify this?
Yes, sine squared.
Yeah, we ain't doing that. We're going to integrate this like it is. Look at this. I'm going to rewrite this function, or this integral. Because I can factor a 1/2 out, and I'm left with 1 minus cosine 2t dt, right? Pull that 1/2 out in front. And then I've got the integral of 1 dt minus 1/2, because it's out front. Or I could just leave it in brackets. The integral of cosine 2t dt, and these both go from 0 to pi over 2.
So the 1/2 came from the 1 over 2.
The whole thing was over 2, so I factored that 1/2 out. It's not just 1 over 2. This is being divided by 2 as well. That's why I said it's 1/2 times this. I'd have to distribute that 1/2 to both of these. Look, I can make it real easy.
I understand that. I just don't understand why the 1's still up there if you brought it out to the side.
I didn't bring the 1 out to the side. I brought the 1/2 out to the side. This is the constant term that came out front.
It's 1.
Watch. It's 1/2 times 1 minus cosine 2t dt. And that's 1/2 times, and then I distributed the integral across this subtraction of 1 dt minus the integral of cosine 2t dt. Okay, does that help? All right, when we integrate 1 with respect to t, what are we going to get? T. You can check to see if you've got the right antiderivative by taking the derivative. The derivative of t with respect to t is 1. When we integrate cosine, we get a positive sine 2t, but we also have to put the 1/2 there, because when I take the derivative of this, remember I got to go back to that, and the chain rule says you have to multiply by 2, so we put this 1/2 here to counteract the multiplying by 2 when we take the derivative. And this is then evaluated from 0 to pi over 2. So this is going to be 1/2 times, we're going to plug in which of these first, the 0 or the pi over 2? The pi over 2 goes first, so this becomes pi over 2 minus 1/2 sine of 2 times pi over 2. It's your upper bound minus the lower bound. 0 minus, sorry, probably should have done that, but 0 minus 1/2 of sine 2 times 0. And now we take care of the arithmetic. I'm just showing every algebraic step I can. So this is 1/2 times, this is pi over 2. Sine of 2 pi times pi over 2 is sine of pi, and sine of pi is 0, and 0 times 1/2 is 0. So my upper bound gives me pi over 2 minus my lower bound, 0 minus 0. And that's going to be then, no, positive pi over 4. Because all of these zeros don't do anything with the addition and subtraction. This is 1/2 times pi over 2. Because pi over 2 minus 0 is pi over 2. Minus the 0 again is still pi over 2. So this is pi over 4. I put it in red so you know that's the final answer. 1/2 times pi over 2 is pi over 4. Then we've evaluated a definite integral. We've grown up, boys and girls. We're doing big boy math, big girl math. Okay, can we evaluate this definite integral? One of the things you want to know is you need to simplify your integrand before you ever try to integrate, because this thing looks horrible, doesn't it? So we're going to rewrite this as the integral from 1 to the square root of 6 of, distribute that denominator. It's going to be s squared over s squared plus s to the 1/2 over s squared ds. All I did was I distributed the denominator. You're allowed to do that. When you add fractions, if you have a common denominator, you just combine the numerators. Well, I'm undoing that adding of the fractions. S squared over s squared is going to reduce to what? So that's 1 plus s raised to what power? Negative 3/2. No. 2 minus a half is 1.5, which is 3/2. ds. Well, I can distribute the integration across the addition and subtraction, or what we can do is just integrate it a term at a time, because isn't that what we did with derivative? We didn't distribute the derivative every time. We just find the integral a term at a time. So when we integrate 1, what do we get? And when we integrate s to the negative 3/2, we add 1 to the exponent. So that's going to be s to the negative 1/2 divided by negative 1/2, and we evaluate this from 1 to the square root of 6. Is that right? So this is going to be just working this out. S plus negative, it's actually going to be s minus, because a positive over a negative is negative, 2 over the square root of x. Right? And then s from 1 to the square root of 6. Right? Fundamental theorem of calculus says we plug in our upper bound. So that's going to give us the square root of 6 minus 2 over the square root of 6. Well, the square root of 6 is 6 to the 1/4, isn't it? It's the 4th root of 6. Minus, plug in your lower bound. 1 minus 2, right? Because the square root of 1 is 1, and 2 over 1 is 2. Okay, cleaning this up then, we get the square root of 6 minus 2 over the 4th root, we'll do it like that, of 6 plus 1. Typically, we don't want to leave that radical in the denominator. So I'm going to have to multiply this term by what? 6 raised to the 3/4 over 6 raised to the 3/4. See, this is 6 to the 1/4 power, right? And I need to multiply by this by something so that the power here is 1. Well, what can I, when you multiply with a common base, you add the exponents. So that's going to give us the square root of 6 minus, that 2 will cancel with the 6 in the denominator then, and this is going to be, we could write this the 4th root of 6 cubed over 3. That'll work. Plus 1. This is the exact value. If I asked for a decimal approximation though, what would you do? Put in the calculator, and I wouldn't have tried simplifying that denominator at all. Odds are though, I'm going to want the exact value. Now, I'm going to show you, hopefully if the computer doesn't crash because I opened the calculator, I'm going to show you how you can evaluate these on your calculator. Y'all both have your 89s with you, right? Y'all mind sharing the 83 so you can see how to do it, because this is what you got to use for your test. View, I don't want to see the keystrokes. All right. underneath math, there is a thing that says, I think it's under math, I haven't done this in a while. Function integrate. And you hit enter. Now I got to remember the order that you type this in. I believe it's the function, the variable, lower bound, upper bound. We're going to go with that and see what we get. So this, after we simplified it, we got 1 plus, you got to use an x here, raised to the negative 3/2, right?
Oh, mine doesn't look the same as yours.
Probably not. Let me see yours. You've probably got the newer operating system.
Yeah, 84.
Yeah. It depends on how new it is because the operating system is different.
Okay.
Then you're taking the integral with respect to x, comma. Your lower bound here was 1, comma. The upper bound is the square root of 6.
So what about
Okay, hang on. I'll look just a second. So we get 2.171. Now we can check our answer by doing this. Let's evaluate the square root of 6 minus 2 divided by, or let's just do this, 2 times 6 raised to the negative 1/4. Because it's the same thing as over 6 to the 1/4. And then plus 1. I hit enter. And notice you get the same thing. So the answer that we got numerically or algebraically is exactly the same as what the calculator gives us if we use the integration feature on the calculator. Oh, well yours is easy. It gives you, it looks just like, you just type it in.
How do I type in the negative to the power?
You don't. That's what you want to integrate. You want to evaluate. Well,
Oh,
what
the
I'm
dx.
doing is I'm evaluating this.
Okay.
But why did you do 1? Oh.
1 plus x.
Oh. Raised to the negative 3/2. So x
The caret sign, right?
raised to the
Okay.
negative 3
What about 2?
divided by 2.
Inside the parentheses.
Yeah.
I told you that.
And it's beautiful. It looks like that. So your function right here, you put in this.
Okay.
Oh,
Cool.
awesome.
So the new calculators actually show you something that looks like
An actual image.
an actual integral. So you would put this in. Now, if you're not sure that you simplified this correctly, you could go back and put this integral into your calculator. It's just going to be more cumbersome. We simplified that thing algebraically, and we did it correctly because we showed our work. And it's easier actually to evaluate this. If you have the newer operating systems, it probably looks just like y'all's 89s, where it shows you the actual integral. So, but because you're going to be using my calculator during the test, you need to get familiar with what it looks like. Okay?
Do we have to use that integration function or whatever?
You don't have to use it, but it's a good way to check your answer to see. Because whenever I ask for the exact value, you're either going to give me this or you're going to give me this. Okay? That's the exact value. And I will dock points big time if you give me a decimal approximation. Because I know you can do it on the calculator without thinking about calculus. All right? And I'm not going to give you credit for that. All right? But it's good to check yourself as you go along. All right, example 4, evaluate the definite integral. We're going to do this symbolically or algebraically. We want to get the exact value. Got it? All right, so what do we do with our constant? So this becomes 3 times the integral from 0 to the natural log of 5 of e to the 2x dx. When we integrate this, it's going to be 3 times what? But when we take the derivative of that, we're going to have a 2. We got to undo the effect of the 2, so that gives us a 1/2 e to the 2x.
So you can work out.
Yeah, when you take the derivative to check yourself to make sure you found the correct antiderivative, when you take the derivative of your antiderivative, you've got to get the original integrand back. So when I take the derivative of e to the 2x, I get e to the 2x times 2, because you got to take the derivative of the exponent. So that 1/2 here is here to offset the effect of that 2 in the exponent. And that's one of your rules on the list of rules for antiderivatives that was back in, I don't remember what section. Huh? You divide by the constant in the exponent. Yeah. All right, so now we have to evaluate this integral because we were asked to find the value of the definite integral. And I'm going to pull that half out because it's just a constant. So that's going to give us 3/2 on the outside. And then we get e to the 2 times the natural log of 5 minus e to the 2 times 0. So this becomes 3/2 times 25 minus 1. I knew you were going to ask that. I'm so glad you did. The power rule says that when you have 2 ln 5, you can take that 2 and move it up into the power here. So that becomes the natural log of 5 squared. And when you have e raised to that power, these are going to end up canceling out. And you get 5 squared, which was 25. And this was the inverse property. For exponents and logs, just to remind you of those algebra rules. 25 minus 1 is 24. 24 times 3/2 is 12 times 3, or 36, right? Very cool. You can do this on your calculator as well to check yourself. However, on your test, you have to show your work. So, the next thing we're going to look at then is the definite integral as a function of x. All that we do here is we say we're going to replace one of our bounds with x. So the derivative of the antiderivative is going to be the derivative of the integral. And when you have an upper bound of x here, you're going to end up with a function of x. So example 5, we're asked to find dy dw for y equals the integral from 0 to w of 8, the square root of 8 plus 9t squared dt. Based on Theorem 4, which is the first part of the fundamental theorem of calculus, this is going to be the integral, not integral. This is going to be the square root of 8 plus 9w squared. When you take the derivative with respect to a variable of an integral where the upper bound is a variable, all you're doing is you're trading out those variables, the t and the w. That's the first part of the fundamental theorem of calculus. Haven't seen this one come in too handy for any reason other than doing proofs. Okay, so if you're a math major and you're going to go on into advanced calculus, you may need to know this in order to do some proofs. Working mathematical proofs and advanced calculus proofs. In the real world, a practical application, none. Theoretical, yes. Okay, so all you engineers can rest easy. All right, so to find the area between the graph of y equals f of x and the x-axis over an interval, what we're going to do is we're going to subdivide, if our function dips below the x-axis, we're going to subdivide this function into 2 different integrals because we have a positive area and we have a negative area. And when we add the 2 areas together, if the instruction said just find the area between the graph of the function and the x-axis, We don't want negative areas. I said integrals can have negative values. If your function is negative, like it is down here, you're going to have a negative value for your integral. So what we do is we take the absolute value of that negative region, which means that you have to know what the graph of the function looks like. So in example 6, we're asked to find the total area of the region between the x-axis and the graph of y equals negative x squared minus 3x on the interval from negative 6, 1, 2, 3, 4, 5, 6. So that's this region right here, all the way up to 1. So that's this area here and this area here. So we have a total of 3 regions that we're going to have to evaluate. So this is going to be the integral, when I set this up, for this first region, goes from negative 6 to 1, 2, 3, negative 3 of negative x squared minus 3x dx. Plus, then we have the integral from negative 3 to 0 of, that's not going to be a plus, no, that is plus. We're going to have the opposite of this, because this is going to be a negative value, right? So we're going to have the opposite. You with me? Plus, because this area is positive, negative x squared minus 3x dx minus the integral from 0 to 1 of negative x squared minus 3x dx. Okay? These areas right here and right here were negative areas. So we wanted to use the opposite of those areas so that we end up with a positive value. Does that make sense? We can't just integrate from 0 to negative 6 to 1. That's not going to work. We won't get the right value. Areas are always positive. Okay? So when we end up with a negative area, we're going to force it to be positive. So this ends up being, what can I do to offset that negative? That's just a negative 1, right? I'm just going to distribute it across this function. So this is the equivalent to the integral from negative 6 to negative 3 of, when I distribute that negative, I get x squared plus 3x dx plus the integral from negative 3 to 0 of negative x squared. Actually, I can pull that negative out. And we can make it minus the integral from negative 3 to 0 of x squared minus 3x. And then pull the negative out here, and that would be plus the integral.
You pull the negative out of that term, wouldn't that 3x be plus 3x?
Yeah,
X squared plus
it
3x?
is. Calm down. I just made a mistake. You're right. All right. So now we evaluate these integrals. Then when you integrate x squared, you get 1/3 x cubed, right? Plus 3/2 x squared from negative 6 to 3 minus 1/3 x cubed plus 3/2 x squared from negative 3 to 0. Plus 1/3 x cubed minus 3/2 x squared from 0 to 1. Question?
Instead of writing it negative, can't you split the lower bound and the upper bound and do the same?
You could have, but I'm happy getting those negatives out of that integram. Very happy.
But you don't have to have
No.
it. You split the-
You still have negative numbers in your bounds. But see, there was a negative x cubed minus 3x. I wanted to pull that negative out anyway. So, but doing what you said will get you the same place. Your work would just look a little different on the trip to get there. Okay, so let's go ahead and evaluate this. What do we plug in first, the upper bound or the lower bound? Upper bound. So this will be negative 3 cubed. I'm going to do it like this. This is 1/3. Let's do this. Negative 3 to the third over 3 plus 3 times 3 squared, negative 3 squared over 2. I'm just putting my x's up there in the numerator with the 1 and the 3. That's my upper bound minus my lower bound. So this is going to be negative 6 cubed over 3 plus 3 times negative 6 squared over 2. All of this right here is the values of this first integral right here. And then we have to say minus, yikes, I'll do the next one in blue, 1/3, or let's do, this is going to be a 0, because we're going to plug in our upper bound. The upper bound is 0, so that's going to give us 0 plus 0. Are y'all okay with that? Because I already know that's what it's going to be. Yes, no, maybe. Minus your lower bound, which is negative 3 cubed over 3 plus 3 times negative 3 squared over 2. So far, so good? Plus and then we're going to use the green. This is going to be negative, no, upper bound. Can I just write 1/3 minus 3/2 for this one? You'll see that's what it's going to be when I plug in a 1, right? 1/3 minus 3/2 minus 0, because when I plug in the 0, I'm going to get 0. And then we just simplify. So this is negative 9. Yeah, because negative 3 is negative 27, divided by 3 is negative 9, plus 27/2, plus, because when I cube a negative, I'm going to get a negative. This is 6 cubed. What is 6 cubed? I know, but what is it? I don't know. Somebody's got a calculator out. 6 cubed, 316 plus 316 divided by 3. Does that go evenly? It's got to. Divided by 3. Huh? 72. Thank you so much. Minus 3 times 36 divided by 2. That's 3 times 54. Minus, because I got to distribute the negative, 0. And a negative there is going to make that plus a negative 9 minus, huh? Well, that negative right there would cause it to be a plus, this one right here, because that's going to be a negative, but there's a negative outside the bracket as well, so it's a negative 9. All right, and this is going to be 3 squared, so that's going to be 27 over 2, and it's going to be positive, so that's plus 27 over 2. And then we have plus 1/3 minus 3/2. Will any of these combine or cancel out nicely? 27 over 2 plus 27 over 2 are like terms. We get negative. I'm going to combine the 9s. So that's negative 18 plus 27 and 27 is 54 divided by 2 is 27. And plus 72 minus 54 plus 1/3 minus 3/2. Somebody with a calculator, add all that up for me. How many?
25.83.
I'd rather have a fraction. Thank you. That's the exact value, 155 over 6. The 0.83 with the decimal repeating is a decimal approximation. And we're done. Example 7 we don't have time for. That's it. And I didn't finish putting in the example, so good enough. We're done.